I've been with this community for quite a while. We've talked about various exciting topics in the past, from drones to high voltage things, plant power, and various design thinking challenges. Now, this year, I'll be talking about the experience we have as a development company building solutions for, let's say, larger corporates and industrial clients. And the topic is dual band 868 and 2.4 operation for medical and industrial applications with the range and throughput in mind. Now let's dive into this, let's say, slightly controversial content. So we have the industrial challenge, which you might not typically think is suitable for LoRa. So the challenge is we're building a device which has a display on it. We want to show some things to the users. We have a device with the sensors on it, which show real-time values for whatever values we're reading. We need very quick updates of these values in the cloud because it's tied into a real-time system. And we need to install that in a large industrial or commercial or medical building where we need to cover a large area with as few gateways and infrastructure pieces as possible. Now, the real challenge comes into the way things are deployed, because we need to get this operational without the IT department being too involved in the process. And we need to operate without any recurring costs. Now, what might be a good technology choice for such a project? In a typical scenario, you would consider being very responsive. And by being very responsive, it means when user clicks something on the cloud or in the interface part, which is not on the device itself, that the action is propagated to the device quickly enough. We have the need for the devices to send updates very, very often, preferably about every minute or even faster if we can. We want to deploy as few gateways as possible to minimize the rollout complexity, and it cannot be a mobile network because we have the need to have no recurring costs per device, but maybe as just the whole infrastructure operation. So maybe private 5G networks come to mind, but in all cases, that does not fit the need. So the question is, could LoRaWAN meet the requirements for what we're doing? And we have this interesting chart of various technologies, how we can compare one to the other. So we see the two axes, where we have the short to long range, and we have the throughput from low to high. Now, for the application I've described in the beginning, your typical choice might be Wi-Fi. You can send data reasonably quickly, it's low power enough, and there's no really limit to sending a few pieces of information quickly, and the throughput is high enough. You could do things with the Bluetooth as well, being much more low power and much more constrained in the throughput. You could do things with LoRaWAN at 800 or 900 megahertz as we're used to, where we have an extremely large range and very good coverage, but on the throughput side we might be quite limited. And if we had the cellular network available in such a choice, we could go there as well. Now what we see here is that there is a gap in between these technologies. This red circle in between, which neither of them covers very well. However, if we use LoRaWAN in the proposed dual frequency band configuration, we can fill this spot in. So that's what I'll be talking about more today. With the dual band operation, we can do a few things. So firstly, let's battle them, one to the other. Which one does what better? So we see that the lower frequencies, so 868, 915, are excellent for indoor coverage and deep penetration. So for example, for a reasonably large factory building, or even the venue where we are today, one gateway will very well cover the whole building, no problem at this band. However, if we're in Europe, we can't really send much data to meet all the requirements. There's a few scenarios that are available to us. For example, we can send 222 bytes in about 96 messages an hour at SF7, or worst case, we can only send 12 messages an hour at SF12. However, on the 2.4 gigahertz band, we can really do as much as we want, as there's no duty cycle limitation. We have high throughput. So the only part that's really limiting us is if we put the RX window 1 and 2 of the LoRaWAN to the minimum, we can send about one message every 2.5 seconds. So we can send more than 1,000 messages an hour, which gives us a lot of capacity to use in the real world. So what happens if we combine the two? We get the range of one and the throughput of the other one. Now the two combined can be done in various different ways. We can go down the complicated route of creating a handover procedure where we take messages on one band, messages on the other band, decide what's available, and send things that way. But actually, there's a simpler possibility, which is we create our message structures in a way where on the lower band, we can send heartbeat messages. They're about every 300 seconds. If we do it at SF12, maybe ADR can take us to a different spread factor and we can send it faster. Those are our reliable coverage messages. Those are the messages we will know we will receive in any case, and it's a really low probability data won't come through. So this gives us really the critical range, which is needed for a lot of medical and also quite some industrial applications. However, for these applications to work pretty well, we want real-time data. And with real-time data on 2.4 gigahertz, we can get it there about the 2.5 seconds. So with that, we combine the maximal coverage in range and best effort full-speed data service for the two. Given that also we know when we expect messages on the cloud side, on the gateways, we can quickly know when the device is falling out of coverage, and we can alert the users, hey, this device is not being full-time monitored, but you will get an update in 5 minutes, and if you don't have an update in between, go there manually and check things. Which, for example, for safety critical applications can be a very good insight. Now, let's talk about range. We compared the range of the two technologies and did measurements in the field. So here, I'm showing an example where we have a building of about 50 meters long with many rooms and many walls in place. So we took the 868 and the 915 megahertz. I'm sorry, the slides are being slightly cut due to the projection format. So the key part is we run the 868 megahertz at the SF7. So we get the worst case performance, so the worst possible coverage for it. And we run the 2.4 gigahertz at SF12, so we get the best case coverage for 2.4. And now we compare the two. We will see that there is about a good 10 dB difference of 2.4 being worse than 868. However, both successfully cover the whole building, which is a typical reasonably sized industrial building, meaning that, yeah, both will operate well. 868 will provide really reliable coverage, and 2.4 best effort will work quite well. We don't even expect any messages to be lost in it. So if we look closer at the diagram, you will see the black line, which is the outline where we mapped. So obviously the whole building wasn't mapped. We can see the gateway on our right, and we can see how the coverage propagates through the building, and the slight color difference in between the two. The key lessons we learned here is that we need to explore the rollout strategy with our final client and how this gets put in the field. And this is where most challenges actually lie. We see that, for example, putting up one gateway per floor or per building might be quite fine. You can plug it into the wall somewhere. You can see that, for example, if you wanted to roll out a Wi-Fi network where you need to rewire part of the building, it's reasonably impossible and no one will go for it, and your clients will say, no, we're not using this. We can see that the dual band operation is really practical if we want the range and the throughput. And we're quite surprised how well 2.4 gigahertz LoRa actually works in buildings. We expected much less from it, but even compared to Bluetooth and the other technologies, it does propagate significantly far, and with the right settings, we can somewhat compare it to 868. So today, you know, where you have a good, SF7 coverage with 868 in a building, you're likely to have 2.4 gigahertz coverage as well. which will give you a lot higher data throughput. Now, let's see what new opportunities this unlocks. While we were exploring this for this one use case, we found out quite a few new things we can do with this. Particularly when we get artificial intelligence involved, we can talk about vision, sound, and also electrical signals or signals of other sorts. And sending images via LoRa and LoRaWAN has always been like a big no. Don't do this. Scary territory, which is still the case. We don't recommend you doing this. However, there's quite some applications where you might want to do things of this sort. We also talk about the human interface solutions. So obviously, you won't be streaming video to the devices anytime soon with this technology, but maybe you have e-paper displays or some like work orders you need to send to the machines, which if they update within some seconds or up to a minute, it's perfectly fine. Or you have a bunch of devices in a medical institution where you need to, say, upload a recipe or some number of values. You want that to reach the device reasonably quickly, so when you place something on the cloud, the device quickly enough blinks and starts doing something. But at the same time, you want this to be convenient and available for everyone. So what are the unlocking applications? For example, sending images. The big scary thing. Well, we see that while cameras take high resolution images, these days, in most cases, machine learning models will operate on scaled down images. 160 by 160, 720 by 720, or some small number of pixels. In most cases, we just want to send the machine learning output. So, probability of seeing a spiky turtle in an image, how high are they? A number between 1 and 100%, which is excellent. However, when we find something interesting, or particular where we want to send an alert to the user, where the user needs to validate that what the system is saying, alert, something's wrong, is it really wrong? Usually you need a human confirmation in the process. And then if you can send a small image, a downsized image to the user, they can check it, it's really good. So let's look at some particular numbers. The two images here, we see a small one and a slightly larger one. One is 6 kilobytes, the other one is 56 kilobytes, JPEG compressed images. So if we look at, for example, the 2.4 gigahertz band, we will see that within a reasonable time we can send these images. On the 868, well, might take the whole hour to send an image. Or good 10 minutes, not exactly what you want to do. However, if you happen to be in very bad coverage, you might still have that option. A more complex example is using FOMO. So this is object detection, example from the Edge Impulse here. How this works is you take an image, you split the image in 8 by 8 pixel squares, or some number of small pixels, and you run a machine learning process on each of those squares of the image. On the screen you will see the grid here. And the machine learning model will return us the probability of something interesting being in each of the squares. So what turns out from the whole image, you need to send only a few chunks with the position which have something interesting on it for the human validation. So you end up with a few of 8 by 8 pixel chunks, and with 1 kilobyte of chunks, you can send it with 2.4 gigahertz in about 15 or 16 seconds. That can be a pretty good user experience to validate something or show up on the screen. And we can do the same thing with audio. We're not sending real-time audio or anything like that, but most machine learning models will run on real-time data, but in windows. So you'll have a 100 millisecond window, which you move in 50 millisecond increments, for example. And only some of those 100 millisecond chunks will have some interesting data in it. And once you find something unknown, say a click or a gunshot or some short event, you send that chunk. It will take a few seconds to send it over the 2.4 gigahertz, and that's it. In most cases, you will be in coverage. In any case, you will send the results over 868 as well, and you will have almost guaranteed delivery in that case. So combining that from all the perspectives, we see this particularly for medical and industrial applications. there's a lot of focus on fast and reliable delivery, very good coverage with minimal infrastructure involvement, and particularly real-time and critical things where they need to happen. And dual band operation is something which unlocks these opportunities. One band and the other band standalone don't necessarily cover the application, but this combines it perfectly for us. Feel free to reach out to me with any questions. I'm giving another talk in a panel on the other stage in just a minute, so I won't really be available for questions here, but you can find me later on the IRNAS booth. So thank you very much.